Hello everyone, I'm João from That's Brilliant, and in this video we're going to talk about the area of a circle or the area of a disc, and we're going to see the mathematical proof of the equation that gives us the area of a circle. So what's a circle? Well, it's very intuitive. We have that shape, right? And this is a circle. So this curve around the circle, this thing right here, and I'm not drawing it exactly over it, but you can get the idea. This around the circle, this is the circumference, and this is just the circumference. The circle is the circumference and the internal area. So this is the whole circle, this is the whole disk. And we want to prove the equation that we use to calculate the area of this shape, the area of a circle. And remembering the equation, let's call the area of the circle A. So A equals pi r squared, where r is the radius of the circle, so a point from the center of the circle to a point in the circumference. This is the radius. And pi is a mathematical constant. Pi is approximately 3.1415 and so on. So this is the equation that we want to prove. And there are more than a way to do that. And in this video, we're going to prove this equation in a very simple way. And we are going to have future videos proving the same equation differently. But this proof here is very simple. So let's start it. Imagine we have a circle, and we are going to divide the circle into many triangles. So imagine you do this. We have some triangles, and I mean, this is not a triangle yet. This is a triangle. Okay, we have these triangles here. And my drawing isn't perfect, but please use your imagination. And this is a circle divided into some triangles. And notice that if we calculate the area of the triangles and add them up, we are not going to get the area of the whole circle. Why? Well, because this difference here is not we're not counting this difference here. There is a difference between the area of the triangles and the area of the circles. But now imagine we have the same circle, but now we're going to divide the circle into more triangles than we did in the first time. More triangles, and they're going to be smaller. So we have, for example, this. We're going to have more triangles, and so on. We're going to have more triangles, and they are going to be smaller than they were in the first circle. The circle has the same area. We're just dividing the circle into more triangles, which are going to be smaller. And the triangles are, let me use the blue. The triangles are here, more or less right here. And we can see that if we add all the areas of all the triangles, we are not going to get the exact area of the circle, because we're not going to be counting this area right here. But there is something we can see, that the difference between the area of the triangles, the area of the circle, is smaller than it were in the first circle. So if you calculate the area of these triangles right here and sum them up, they're not going to be the area of the circle. There's going to be a difference. But the difference here is greater than the difference right here. You can see that the difference here, the black part, which is the part that's not counted when we add all the areas of all the triangles, this difference is smaller. So we can see that the more triangles we put inside the circle, the closer the areas of the triangles are going to get to the area of the circle. So we're going to divide the circle into even more triangles. So imagine we have the same circle, and we're going to have even more triangles. And I cannot draw this as narrow as we are imagining. This is just to give you an idea. And let's say we are dividing the circle in n triangles. And as I said, imagine these triangles are very, very small. We have n triangles, and this n here is very, very large. It's a very large number, and it's approaching infinity. And we have a lot of triangles, many triangles, which are very, very narrow, And as I said, I cannot draw the triangles as narrow as we are imagining them. This is just to represent, but imagine this even narrower, even more narrow. So something we can see, maybe this remembers you of calculus, and this is an idea that we can apply calculus to. But we are not going to use calculus in this video. As I said, this mathematical proof is going to be very simple. But maybe in future, maybe in the other mathematical proofs of the area of the circle, we can use calculus. We're going to have more videos about this. But as I said, we're going to just use this idea, but we're going to make it very simple. So moving on, let's calculate the area of one little triangle here. And let's say we have this triangle. I'm going to draw one of them right here. But now I want to have it bigger, just because it's going to be easier for me to draw. But notice that this is the same little triangle. I'm just drawing it bigger to make it easier to draw. So we are not using a bigger triangle. We are just zooming in the little triangle. So if you pick one of these little triangles and zoom in, you're going to have the same little triangle, but a little bigger. So let's calculate the area of one little triangle. And remember, it's little. I just draw it bigger because I was zooming in, because it's going to be easier for me to draw. But this is the same little triangle we had here. So we can see that this length here is a radius. This other length here is also a radius. These two lengths are radius because they are lines that go from the center of the circle to a point in the circumference. And also, this line here from the center of the circle to a point in the circumference is also a radius. But remember, we are using a very, very narrow triangle. The triangle is very, very small. So this difference here is so small, but so small that we can ignore it. And instead of calling all this length of radius, we're not going to do that. We're going to say that the radius is just from this point to this point right here. And why we can do that? We can do this because we can see here the difference between the triangle and the circumference is big. When we had more triangles, this difference was smaller. We have here infinite triangles. We have so many triangles, but so many triangles that this difference is so small that we can ignore it. We can consider this difference equal to 0. And because of that, we can call this length of r. And now we can calculate the area of one little triangle. So as we know that the area of a triangle, let's say the area of a triangle is base times height divided by 2. And so let's do this equation to one little triangle. So the area of one little triangle is going to be the base. And what's the base? So let's go back to our circle. Here, the base, we have, first of all, let's go to the circumference. A circumference, you can calculate that as 2 pi r. This is the length of a circumference. But as we were saying, this triangle is so small, but so small, that this difference can be ignored. Another difference can be ignored. We can say that this triangle is so small that we can consider that the length of this little arc is the length of this straight line. And this straight line is the base of the triangle. So we have the circumference is 2 pi r. We have divided this circle into n triangles. So each triangle has underneath it here 2 pi r over n. The length of the arc under a triangle is 2 pi r over n. Why? We have 2 pi r total circumference. And we have any triangles, and each triangle has a part of the circumference under it. So we have a total of 2 pi r, and we have divided into n. So this arc here, the length of this arc is 2 pi r divided by n. The length of the arc is under one little triangle, 2 pi r over n. And as I said, this difference is so small, the triangle is so small, that the difference between the length of this straight line and the length of the arc can be ignored. We can consider that the length of the arc is the same of the length of the straight line. Okay, consider that the difference between these two lengths is equal to 0. So we can say that the base of the triangle is 2 pi r over n. And now times height. What's the height of this little triangle? As we saw, this is from this point to this point in the base, which is r. And we divided by 2 because the equation of the triangle has this divided by 2. Now we can see that this 2 here cancel out, and we have the area of a little triangle is pi r squared over n. And if we add all the areas of all the little but very little triangles, we're going to get the area of a circle. So how many triangles we have? We have any triangles. The difference between this difference here can be ignored. So we have so many triangles, but so many triangles that the difference between the difference between the area of all the triangles, the area of the circle, can be ignored, because I have so many triangles that these little differences can be ignored. So we can consider that the area of all the little triangles summed up is equal to the area of the whole circle. So what's the area of all the little triangles summed up? The area of one little triangle is pi r squared over n. So pi r squared over n. And here we are calculating the area of the circle. Let's call it, as we did the first time, let's call it A. It's the area of the circle. This is the area of one little circle. One little triangle. And how many triangles we have? We have any triangles. So n times the area of one little triangle gives us the area of all the triangles summed up. And as we have already talked about, this is going to be equal to the area of the circle. So the n cancel out, and we have that the area of a circle is pi r squared. And this is the area that gives us the area of a circle. And maybe this has not convinced you, because we have ignored a lot of things. And you have total right of doubting about this. You can be skeptical about this, because we have ignored some things here. But this is correct. This equation is correct. And as I said, this is a very simple way of proving this. Very simple. And maybe that did not convince you. And you have the right of being skeptical about this. This can be very confusing. But as I said, this is a very simple way. We're going to have more videos proving this mathematically and with more formal mathematics to prove, with more with a more solid proof that this equation is correct. But as I said, it's correct. We're going to have more videos proving this in a more solid way. So thank you very much for watching, and I see you in the next video.